emission lines across the galaxy, and so you can identify, for example, regions dominated by radiation from an AGN and distinguish them from regions dominated by star formation. You can also use the Doppler shift as well as the width of the emission lines to see what's going on with the gas kinematics. So in these galaxies, for example, you can see that we're seeing rotation, so there's clearly some sort of disk-like structure. And in these two galaxies over here, there's a high degree of turbulence in the interstellar medium as well. So it's a very powerful technique. And in particular, optical interfield spectroscopy is a key tool for us to enable to study the baryon cycle. So because it provides us with spatially resolved ionized gas kinematics, we can trace things like star formation, inflows, outflows, accretion, you name it. So the data I'll be talking about today comes from the SAMI Galaxy Survey. So this is an integral field spectroscopy survey that covers over 3,000 nearby galaxies. The survey instrument itself is shown here. So it's a fiber bundle spectrograph instrument. So here is a schematic showing the fiber bundle placed onto a typical galaxy in the survey. So basically each of these round circles represents a fiber, and so you get a spectrum in each of those fibers. And so you can really spatially resolve different spectra in different parts of the galaxy. The instrument itself is mounted on the Anglo-Australian telescope. It's a 3.9-meter optical telescope located in Siding Spring Observatory. Here's a picture I took of it when I was there one day when it was actually snowing, which is very unusual in Australia. And I also like to acknowledge that the telescope and the observatory are located on the traditional lands of the Kamilaroi people. So a key feature of the SAMI Galaxy Survey is its high spectral resolution. So we're actually able to resolve spectral features down to 30 kilometers per second, especially in the red arm of the spectrograph. But why do we actually care about this? Why is this important? To demonstrate this, here is a toy kind of model. So let's imagine you're looking at a galaxy, and along your line of sight, you have a cloud of gas that is, has a low degree of turbulence, and it's hanging out at the systemic velocity of the galaxy. Now, let's also imagine that along that same line of sight, you have a second cloud, which is entrained in an outflow, and so it's highly turbulent, and let's say that outflow is pushing the gas in your direction relative to the galaxy. Now let's imagine what the emission lines might look like from this simple system. They might look a little something like this, where the emission line that you get from the purple cloud is blue shifted because it's moving towards you, and it's also much broader because it's more turbulent. Of course, when you look at the system using a telescope, you're going to see the sum of these two emission line profiles. But because our instruments are not perfect and they have a finite instrumental resolution, the actual line shape you'll end up with might look a little something like this. In particular, if your spectrograph has low spectral resolution, you may be completely unable to tell that there are multiple emission line components there, which means that you actually can't recover the underlying gas kinematics with any degree of accuracy. However, if you spend a little bit more money or you design your spectrograph differently, you can achieve higher resolution, which means that you can actually start to resolve the asymmetric shape of the resulting emission line. And that means you can work backwards and disentangle these two separate underlying components and successfully recover the underlying gas kinematics. Of all of the current IFE surveys that are out there, SAMI has the highest spectral resolution, which enables us to study gas kinematics in a great amount of detail. And in particular, the spectral resolution of SAMI is more than 2 times better than either Manga or Khalifa. As a sort of technical side note, the way that the fitting was actually done to the data in the survey was that for each spaxel, so each spectral pixel within each galaxy, 1, 2, and 3 Gaussian components were fit to each emission line, and then an artificial neural network was used to determine the optimal number of emission line components that should be in each spaxel. Happy to talk about that in a bit more detail later if anyone's interested. So here's an example of how we can study the baryon cycle with SAMI. So in particular, spectrally resolved emission line profiles can tell us a lot about what's going on with the gas flows in these galaxies. Here is an image of a typical garden variety star-forming galaxy that you might see in the SAMI Galaxy Survey. So on the left here, I'm showing the SDSS RGB optical image, and on the right, I'm showing the velocity field that is traced by the emission lines. On the right here, I'm showing a typical emission line profile from the center of this galaxy. And in this particular galaxy, all of the emission line profiles look something like this. They're very regular, they're very symmetric, and you can fit them all using a single Gaussian component. And so what we're seeing in this galaxy is the thin ionized gas disk. So in this case, the emission lines are actually coming from the H2 region. So this is tracing star formation in these galaxies. However, in SAMI, we detect a fair number of galaxies that look a little something like this. So in this case, the emission line profiles have this blue wing associated with them. And so the neural network has decided in this case to fit 2 emission line components. And if we look at the kinematics of the broad component, we actually see that it differs quite a lot to that of the narrow component. In particular, it's blue shifted and it doesn't appear to exhibit rotation. What we're actually seeing in this case is a wind or an outflow. And so these are caused by intense star formation, and they're believed to be launched by stellar winds and supernova explosions. Winds and outflows are actually quite common in galaxies in the local universe. So most of you have probably seen a picture of this galaxy before that I'm showing in the background. This is M82. It's used as the poster child for galaxies with starburst-driven winds. And that's because you have this beautiful blue stellar disk, and you have these two massive biconical structures that represent gas that has been blown out of the center of the galaxy by intense star formation. Integral field spectroscopy studies of this galaxy have shown quite complex emission line profiles. So, for example, this particular region of the galaxy near the middle, you can see these double-peaked emission line profiles, and these actually trace gas that is moving on opposite sides of the bubble that's expanding. So you've got one that's moving towards you and one that's moving away from you, and that's how you get this line splitting. We see similar examples in the SAMI Galaxy Survey. So this particular galaxy, 209807, has very complex and very irregular emission line profiles. And so the neural network has actually decided to fit 3 emission line components in almost all parts of this galaxy. And if you map out the kinematics of these profiles independently, you can see that the narrow component traces smooth rotation, whereas the broad component is not rotating, instead it's mostly blue shifted, and so this is a vigorous outflow, whereas the intermediate component appears to trace a sort of mixing between the two. Past studies have shown that galaxies with winds tend to be more massive, and they tend to have high star formation rates, as shown by this study from Avery et al. 2021, where the black histograms represent galaxies with winds, and the gray histograms represent galaxies without winds. It's also been shown that winds appear to be ubiquitous in galaxies with star formation rate surface densities above a certain threshold. So in this particular study by Roberts Bolsani et al., they found that galaxies with outflows, which are these blue triangles, all appear to have star formation rate surface densities in excess of around 10 to the minus 2 solar masses per year per square kiloparsec. So that's winds and outflows. However, there's another type of interesting star-forming galaxy that we see in SAMI, and they look a little something like this. So in this particular case, there are many parts of the galaxy which require multiple emission line components, but once you trace out the kinematics of the broad component, it's not blue shifted, it's not red shifted, instead it appears to be rotating, and it looks like it's rotating in much the same way as the thin disk. What we're actually seeing in this case is what we call the thick ionized gas disk, also referred to as diffuse ionized gas, and this is gas that lies outside the H2 regions. And typically, thick ionized gas disks have a large scale height that is much higher than that of the thin disk. And so to go into that in a little bit more detail, diffuse ionized gas and thick ionized gas disks, they mean the same thing, so you can imagine that they're interchangeable. So this is broadly referring to gas that is ionized by radiation from either leaky H2 regions or by hot low mass evolved stars. It was actually first discovered in our own Milky Way, where it's called the Reynolds layer, and it's present as this tenuous H-alpha diffuse background that sort of sits on top of everything else. Recent studies have shown that in other galaxies, the diffuse ionized gas has motion that's dominated by rotation. And if you map out the rotation curve of the dig separately to that of the thin disk, you find that it rotates more slowly and it has a higher velocity dispersion than the narrow component, which tells us that it resides in a disk with a larger scale height. Studies going all the way back to 2003 have also found that dig is more prevalent in galaxies that have higher star formation rate surface densities, which suggests that there might be a connection with winds. And so the current leading theory for where diffuse ionized gas comes from is that it represents recycled gas from galactic fountains. And so it's settled into this sort of turbulent thin disk that should only hang around for as long as you have star formation to power it. So this brings me to the key questions I'm going to ask in this talk. The first is, what actually drives the presence of complex emission line profiles in star-forming galaxies? So why do we see them in some galaxies but not in others? And the second question is, what is the relative importance of local versus global effects in dictating the presence of complex emission line profiles? So how important are global properties, such as things like stellar mass, with respect to local properties, such as the local star formation rate in a particular region of the galaxy? So to start off answering the first question, the first thing I did was identify a parent sample of star-forming galaxies. So without going into too much detail, I basically just wanted to make sure that my galaxies had good spatial coverage, they had good quality data, and that I wasn't accidentally including anything like AGN. From these, I identified 2 subsets of galaxies. So the first was what I call one-component galaxies. So these are galaxies in which virtually no spaxels require multiple components to characterize the shape of the emission lines. So here's an example of a typical one-component galaxy and an example of a typical emission line profile that you might see in one of these systems. On the other hand, I defined what I call multi-component galaxies. So these are galaxies in which a high fraction of spaxels require multiple Gaussian components to fit the emission lines. And so here's an example of a multi-component galaxy, as well as a typical emission line profile that you might find in one of these. So the first step in the analysis was simply to look at, plot a bunch of histograms, figure out if there's any significant difference between these two populations of galaxies. And that's exactly what I did. So I'll go through each of these step by step, don't panic. Basically, in each of the subplots, the multi-component galaxies are represented by the dark outline histogram, and the one-component galaxies are represented by the shaded blue, and the whole 3,000 galaxy sample of SAMI is represented by the black. So that's sort of, the parent sample. So at a glance, the multi-component galaxies are more massive, as you can see here. They have higher star formation rates, significantly higher star formation rate surface densities, regardless of which aperture you measure that in, and also higher specific star formation rates. They tend to have similar sizes, but because they're more massive, that means that if you divide the stellar mass by the effective radius, that value is larger, and that's a proxy for the gravitational potential, and so we can infer that the multi-component galaxies also have stronger gravitational potentials. By a similar vein, they also have higher stellar surface density, so that's the stellar mass divided by the square of the effective radius. And they also appear to have redder colors, as well as higher Gini coefficients, which is a measure of how centrally concentrated the star formation rate is. So we might be tempted to look at these histograms and think that, okay, well, maybe, stellar mass is what fundamentally drives the presence of complex emission line profiles, but then it might also be star formation, but then it might also be how concentrated the star formation rate is, right? So it's not really simple. So I showed, for example, that the multi-component galaxies are more massive and they have higher star formation rates than the one-component galaxies. But we know from, decades of studies that stellar mass is itself correlated with star formation rate. So to show you an example of that, here I'm simply plotting the one and the two component galaxies on the star formation rate main sequence, where we just simply have star formation rate as a function of stellar mass. And there's a really strong correlation there. And again, this has been documented for decades. And so what this tells us is that we can't tell from this alone whether star formation might be the most important thing or whether stellar mass might be the important thing. So we have to think carefully about how we can come up with ways to figure out which parameter is actually more important here. Another issue we have to deal with is observational biases. So we know that the multi-component galaxies have higher emission line signal to noise, which is never a good thing. They also have a different redshift distribution, so they actually tend to be a bit more distant, and it's a bit complicated to figure out what effect this is going to have, because that could simply arise from the survey selection function, which underlines SAMI. So again, it's not simple. And again, the one-component galaxies tend to be more edge-on than the multi-component galaxies. And so we also have to come up with a way to deal with all these observational biases. So the question then becomes, how can we possibly determine what is fundamentally driving the presence of complex emission line profiles when we have so many correlated physical properties and observational biases? And here is an approximate representation of what I looked like when I got to this point in the project, and it all just seemed too overwhelming. However, the answer to this came in using a matched sample analysis. So this is a technique that you may not have heard before, so I'll just step through it quickly. So basically, let's imagine that these are our one-component galaxies, and let's imagine that these are our multi-component galaxies. Now, let's say we're concerned about the effect of inclination. So as I showed you before, the multi-component galaxies tend to be more face-on than the one-component galaxies. So one way we can actually control for this is that for every multi-component galaxy, we pick a one-component galaxy that has the same or a similar inclination. And therefore, by building up this subset, we're actually removing that bias of inclination in the sample. And so once we do that, we can simply look at the distributions and other quantities between the galaxies in our matched sample, and that will tell us that whatever quantity we've matched in does not contribute to that particular distribution, if that makes sense. So I'll step through the results slowly. So in each of the plots here, I'm going to show a violin plot. So in this particular case, I'm showing a violin plot of stellar mass on the y-axis, and on the left side of each figure, I'm showing the one-component galaxies, and on the right side, I'm showing the two-component galaxies. The gray kernel density estimate shows the rough distribution of the total sample of the one-component galaxies, whereas the colored kernel density estimate shows what we get once we match in the quantity shown here. So for example, when we match in stellar mass, we're able to match 85 galaxies with one another, and surely enough, you can see that the resulting distribution in the matched samples is identical. So this tells us if there are differences in things like star formation rate or other quantities, we know that stellar mass has nothing to do with it. So let's see what happens. When we match in stellar mass, we immediately see that the multi-component galaxies still have high star formation rates. They have significantly higher star formation rate surface densities by almost an order of magnitude, but they still have higher H-alpha amplitude to noise. So now let's see what happens when we match in star formation rate. When we match in star formation rate, we find that the two-component galaxies are slightly less massive. We also find that, again, the star formation rate surface density is much higher. But again, also the H-alpha amplitude to noise is higher too. We can also match in multiple components as once. So if we match in both stellar mass and star formation rate at the same time, we still find that the multi-component galaxies have elevated star formation rate surface densities. And again, there is also this amplitude to noise effect. Okay, so now let's think about the observational biases. We can match in inclination, we can match in angular scale, which is effectively the same as matching in redshift. And finally, we can match in amplitude to noise. And what we find is that it doesn't matter what we match in, star formation rate surface density is always the quantity that is different between the multi-component galaxies and the one-component galaxies. And what our interpretation of this is that this is a signature of winds and diffuse ionized gas. So as I mentioned before, we know that there is this really close connection between star formation rate surface density and outflows, and this is also known to persist with diffuse ionized gas. And indeed, the examples of the multi-component galaxies I showed you before are clear examples of these two phenomena. So for example, here is that galaxy I showed you before that is dominated by outflows, and here is that one that I showed which is dominated by a thick ionized gas disk. And so this is a nice result because for the first time, we showed using a data-driven approach that you actually can use these multiple Gaussian component fits to infer physical meaning about the presence of winds and outflows and things like that in a large sample of galaxies. So the answer to this first question is that star formation rate surface density appears to be the most important factor that distinguishes galaxies with respect to how many complex emission line profiles they have. And this is consistent with previous studies, which is a really nice result. We can now move on to the next question, which is what is the relative importance of global versus local effects in dictating the presence of complex emission line profiles? So to answer this question, I've split the analysis in two. So I'm first going to start by talking about things on global scales. So this plot here, each point that's going to show up is going to represent a single star-forming galaxy. And on the y-axis, I'm plotting the fraction of spaxels in that galaxy within 1 RE that exhibit complex emission line profiles. And on the x-axis, I'm showing the global star formation rate surface density measured within a 1 RE. What we find is that there is a really strong correlation such that galaxies with really high star formation rate surface densities are far more likely to exhibit large regions that have these complex emission line profiles in them. So there's a clear correlation there. What I'm going to do now is I'm going to look at the same correlation but on local scales. And so on this plot, what I'm going to show is the fraction of spaxels containing 1, 2, or 3 components as a function of the local star formation rate surface density. So basically the star formation rate surface density measured in individual spaxels. And what we find is that if we look at spaxels that have low star formation rate surface densities, we find that basically all of them only require one component to characterize the shape of the emission line profile. But if we start to look at spaxels at higher and higher star formation rate surface densities, we find that higher and higher fraction have 2 or 3 emission line components. And so this is a bit confusing because it's totally possible that the correlation on the left here is actually just a direct result of the correlation from the right. We know that there's this local correlation, and so this global correlation could simply be because the galaxies with high global star formation rate surface densities simply have a lot of spaxels that themselves have high star formation rate surface densities. And so to figure out whether this trend on the left is actually just driven by the trend on the right, or whether there's something else going on, what I'm going to do now is I'm going to show the same plot on the right again, but I'm going to bin the data by their host galaxies' star formation rate surface density. And that looks a little something like this. So in this plot here, the thicker lines represent spaxels that live in galaxies with higher overall star formation rate surface densities. And it's really clear that at a fixed local star formation rate surface density, so here, for example, spaxels that live in galaxies with higher overall star formation rate surface densities are far more likely to exhibit complex emission line profiles than those that live in galaxies with low star formation rate surface densities. And so it appears that there is both a local effect and a global effect at play here. Our interpretation for this is that this is possibly due to geometric line of sight effects. So we know that winds expand laterally once they escape the disk. And what this means is that if you're looking along a particular line of sight towards a galaxy, any wind that crosses that line of sight may not have originated in the part of the galaxy you're actually looking at, as illustrated by this figure here. And this has actually directly been observed in the Large Magellanic Cloud. So in this plot here, the background image represents H alpha emission. So this is basically tracing your H2 regions, your regions of intense star formation. And the circles represent regions where highly ionized winds have been detected. And you can see that whilst most of the circles appear to coincide with these H2 regions, there are quite a few, such as this one here, and this one here, and this one here, which don't appear to be associated with any star formation. And so the interpretation is that the star formation has lots of these winds, and those winds have sort of drifted across the whole galaxy and sort of, smoothed out, been smeared out, and so you're going to see them along lots of different lines of sight. And so in answer to the second question, it seems that both local and global star formation activity are important in determining whether any given region of a galaxy is going to exhibit complex emission line components. And this is consistent with a picture in which winds expand once they leave the disk and spread into different lines of sight. So with both of my two key questions answered, I can now talk a little bit about some future work. So an interesting thing that came up in this work was the fact that we have these galaxies that appear to be windy, and then we have these galaxies that appear to be disky. And so the natural question is, why do some galaxies have winds, and why do some galaxies instead exhibit these thick disks? So as a refresher, here are an example of some wind-like systems. So in these particular galaxies, if you look at the kinematics of the broad emission-like component, they don't tend to exhibit rotation. And if you look at the line of sight velocity offset between the broad and the narrow components, you see that there's often a net blue shift or even a red shift, which tells you that there's some weird non-circular motion going on that could be an outflow. On the other side, we have these disk-like systems where the line of sight velocity of the broad component appears to simply trace rotation. And if you look at the difference between the broad and the narrow components, there is no net inflow or outflow of gas. And so this is all very preliminary, but basically, simplest thing to do is just to make some plots and see if there's anything that jumps out about the differences between the two subsamples. And so in each of these violin plots, the blue side represents the wind-like galaxies and the orange side represents the disk-like galaxies. And quite interestingly, they appear to be the same in almost all respects, except for the wind-like galaxies tend to be maybe a bit less massive. They tend to have higher equivalent widths in the broad component. And they may also be, although only tentatively, a slight difference in the Gini coefficient, which again is related to how centrally concentrated the star formation is. But again, it's really hard to tell because we're dealing with really small sample sizes. One other thing I could do is take this plot and simply overlay the locations of the windy galaxies and the disky galaxies. And when I do that, they also don't appear to inhabit any particular region of the parameter space, which again, I found quite unexpected. One thing I thought to do was to recreate this plot from Eating Ho's work back in 2016, where he basically looked at the strength of these two stellar indices to infer how bursty the star formation history is of these galaxies. And they infer that the galaxies with winds, which are shown by the red points, tend to lie above this line, which suggests that they have burstier star formation histories. However, when I did the same with my data, I found no statistically significant difference between the two subsamples. And so it's still, a very open question and a work in progress. And so again, there appears to be no clear difference in host galaxy properties between the wind and the disk-dominated systems, but this is still a work in progress and it's difficult to draw robust conclusions due to the sample size. Another piece of work that will be really interesting to do in the future is to carry out a detailed kinematic analysis of winds and disks. This brings me to an unfortunate limitation of SAMI, which is that the field of view of each of the bundles is really small. It's only 15 arcseconds in diameter, which actually doesn't reach the turnover radius and the rotation curve in many galaxies. This is a particular case of that, where you can see that the SAMI field of view really cuts off a huge part of the galaxy, and you're really only looking at the middle. And indeed, when you run the kinematic fields through a tool like kinematically to extract the rotation curve, you can still see by the time we run out of data at the edge of the bundle, the rotation curve is still rising. And this really limits the type of analysis you can do. Another downside of SAMI is that the blue arm of the spectrograph has a lower spectral resolution than the red arm. What this means is that you actually can't obtain reliable fluxes for individual Gaussian components in the critical blue lines, such as 035007, H beta, O2, a whole bunch of other lines. And this really limits the type of science that you can do. However, I'm a member of the Hector Galaxy Survey, which is the successor to SAMI. So Hector is going to be bigger and better than SAMI in almost every way. We're going to look at over 10,000 galaxies with Hector, and data collection has already started. Here is a picture of me standing in front of the Hector instrument, also mounted on the Anglo-Australian telescope at Siding Spring Observatory. A key feature of Hector is that the bundles actually have different sizes, and in particular, there are some really big bundles. And so what that means is that you can put the big bundles on the big galaxies and the small bundles on the small galaxies, which means you're eliminating this issue, and you can actually make sure that you're capturing the turnover radius in a much larger sample of galaxies. Another feature of Hector is that we're using a new spectrograph, which has the same red and blue spectral resolution of around 30 kilometers per second, which means we can actually obtain reliable emission line fluxes for individual Gaussian components in the blue lines. This is really awesome because it means that we can probe things like the metallicity, the temperature, the density, the excitation mechanisms separately in the broad and the narrow emission line components in each galaxy. So for my last slide, I just really wanted to show a plot that really drills home the importance of spectral resolution and why this work is simply not possible without it. So in this plot here, I'm going to show a bunch of two-component spaxels from SAMI. And on the y-axis, I'm going to show the line of sight velocity offset between the broad and the narrow Gaussian components. And on the x-axis, I'm going to show the velocity dispersion difference between the broad and narrow components. These lines represent the SAMI spectral resolution. And basically what we find is that there is this unobservable hole that forms, such that if your two emission line components are too close together in velocity and they are too close in width, then you can't distinguish them anymore. And so you're just going to end up fitting a single Gaussian component. Now I'm going to overlay the data on this picture. And you can see that these contours follow the logarithmic density distribution. And you can see that the vast majority of the two-component spaxels in SAMI lie in this region of the parameter space, which really isn't all that far away from the unobservable hole. And if you zoom in, you can indeed see we don't detect any two-component spaxels in this forbidden region of the parameter space. What I'm now going to show is the spectral resolution of manga. So as you can see, the unobservable hole for manga falls right on top of the peak in the density distribution. And so this means that, at least in this particular case, this type of science is not possible with an instrument like manga. And this really drives home the importance of spectral resolution. There's so much really cool science that we can only do if we have it. And SAMI is currently the only large survey that enables us to do this science, with Hector coming online in the coming years. So that's the end of my talk. I'll just finish off with my summary, which is that star formation rate surface density is what drives the presence of complex emission line profiles in star-forming galaxies. Both global and local effects appear to determine the presence of complex emission line profiles in any given region of a galaxy. And again, this science is only possible thanks to SAMI's high spectral resolution. The paper on which this work was based was published earlier this year, so you can scan the QR code if you'd like to read it. And if you're interested in learning more about the Hector Galaxy Survey or you want to join, we're always taking on new members. If you become a member, you're able to access the data before the public will, so it's a great reason to join. Go ahead and scan the QR code down here, and I'll take questions. Thanks for having me.
Thank you very much, Henry. We have time for questions. Very interesting talk, very interesting results. If you have any questions, you can unmute your microphone. Let's see on YouTube as well.
Hello, I have a question.
Yes, Maritza.
So I was wondering if you consider the environment in your sample, like how many of these galaxies are in clusters or in groups?
Yes, that's a really good question. So for the purposes of this study, I didn't, but SAMI has really, really good environmental metric measurements. In fact, there are one of the key science goals for SAMI was to look at, environmental processing. And so there are lots of galaxies that exist in groups and clusters, as well as a large sample that are in the field. And so it would definitely be possible to go back and figure out if there's a correlation between environmental properties and, these emission line component sort of properties.
Other questions? So I have one question. I was wondering if you have any information about the metallicity of your sample. If did you find any correlation between the presence of a wind and any metallicity gradients?
Yeah, so I haven't looked at metallicity gradients. It is really challenging to measure gradients accurately with the resolution and the spatial coverage we have. And by the time, and the other thing with the metallicity measurements is that you need really good signal to noise in all of the emission lines to, use whatever diagnostic you want to use. And so by the time you do that, you're really, your sample gets really, really small. And so it's sort of hard to do this sort of work. I did look at whether the distribution in like the global metallicity measured using aperture spectra is different between the one and the multi-component galaxies, but I found that all the differences can be explained by the mass difference. Like the multi-component galaxies are more massive and they also have high metallicities, and there was nothing else that really popped out there.
Okay, thank you. And do you see outflow in other wavelengths, for example, in the molecular phase or other phase in your sample?
I'm not really sure. There are no large follow-up surveys that target a large number. Getting molecular data, is really observationally expensive, as you probably know. And so you would have to look at individual galaxies. I'm sure there probably are overlaps between some of those surveys and SAMI, but yeah, that's not really my field.
Okay, thanks.
I'm sorry, just a comment on that, but there
Okay.
was a subsample of gamma galaxies that actually they did a compilation of H1 data and actually improved it a lot. So you may actually have some of your SAMI galaxies that match with gamma, of course, and that have H1 information. So
Yeah, yeah. So I know that there are people like Luca Cortese who are H1 experts that are leading the Wallaby survey, and I think they're going to try and target SAMI Galaxy survey targets. So yeah, it'd be really interesting to look for blue shifted wings and things in H1 emission or absorption profiles.
mhm.
I have a
Any
question.
other-
Oh, Mr.
Yes.
Okay.
Patricia.
Thank you for the talk. Very interesting. When you say that the galaxies with multi-components have higher stellar surface densities, in reality, I mean, looking at the histogram here that you have it on the screen now, actually it seems that the histogram is slightly biased towards lower, but I mean, compared with the black one, which I guess the only component is the shadow blue region, no? The ones with multi components is the blue one
Yeah,
and
So this one is the multi-component. This is the one component, and the black is the full SAMI Galaxy Survey. So that includes galaxies of all types. And so yeah, there'll be a lot of early type galaxies in here, which is probably why it looks so skewed.
Okay, that's the first question. But the second one is really, have you looked at locally what is the surface brightness, I mean the stellar surface mass versus the presence of multi-components? I mean, not just the global, because you will expect something local. I mean that locally, no, but in theory, the lower surface, the lower stellar surface densities will allow more winds, no? More, yeah.
Yeah, that's a really good point. I haven't looked into that, but it will be pretty easy to do that because we already have measurements of continuum strength, right next to H alpha, and yeah, so it'll be really quick to check whether that's the case. So yeah, that's a good idea.
Okay, thank you.
Well, I have one last question. And when you mentioned in one of the last slides the difference in the spectral resolution between the blue and the red part of the spectra, did you find any outflow in the oxygen-3 emission line with the resolution you have, one lower than 2000?
Yeah, so
Yes.
so the way that the emission lines are fit is that it's a simultaneous fit across the blue and the red arm. And so it's assumed that all of the emission lines have the same 1, 2, or 3 components. They just have different strengths. The SAMI team officially never released the individual fluxes for the blue lines. And so they only give you the total fluxes. You can only access the individual fluxes for H alpha, which is what all this work is based on. And so, yeah, with the data that they release, it's not, you can't really tell if there are, outflows in the blue lines.
You cannot trust in
Yeah,
that data.
exactly. So there would be some cases where it's extreme enough that you would be reliable to do that, but generally it's not. However, with Hector, that's not going to be a problem. So to sort of give a bit more detail on that. So Hector is a bit of a Frankenstein instrument. It's using the same spectrograph as we use for SAMI, but then there's a second new spectrograph. And so half of the galaxies are in the old spectrograph where you had this difference in the spectral resolution. Then half of the galaxies are in this new spectrograph that has the same spectral resolution. And so for half of the sample, we're going to be able to do this science with the, measuring metallicities and things like that in the, broad versus narrow components. And that's, that goes into the target selection as well. Like, they're trying to put galaxies that might have winds into the bundles that go into the new spectrograph instead of the old one.
Okay, thank you very much.
Can I have a last question?
Yes, sure.
Sorry. Can you give more details about the Hector surveys, like the sample, how it was selected, or if it's yeah.
So I haven't really been involved in the sample selection process.
Okay.
But yeah, I think it's a combination of cluster fields and waves fields.
Okay.
Yeah, with the intention of targeting galaxies that are going to have a really good, multi-band photometry from other surveys and, radio coverage and things like that.
Okay. Thank you.
Okay, well, if there are no more questions, I think we can stop here. So thank you very much, Henry. A very interesting talk and results.
Yeah, thank you so
And
much for having me.
thank you. Thank you very much. And thank you very much for joining us.